So now we'll discuss stability for given system in both S-plane as well as Z-plane. But let's first start with the basic of mapping the given S-plane into Z-plane. So let's first start with the basic. If we consider S-plane, this is in control theory. So this is an S-plane if it is given. There, if you get roots of the characteristic equation on the right half plane, then the system is unstable. If you get the roots exactly on the y-axis, then the system is marginally stable. And if you get it here, then it is stable. Now, how do we map a given S-plane into a Z-plane? Alright, so the equation is Z is equal to e raised to exponential st is equal to e raised to sigma t e raised to j omega t, where this will become e raised to sigma t cos of omega t plus j sine of omega t. So if this is the given S-plane, like this is the S-plane, then this will be its mapped Z-plane, and it goes from here, 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 here. So this is how we map the S-plane into Z-plane. Now for the Z-plane, the condition is if it cuts the unit circle, then the system is stable. If it doesn't, then it's not stable. So to check the stability, there are various tests. First is Routh test. Second is Jury's test. And third is Routh locus. Now, Routh's and Jury's test both help in somewhere in like graphing the Routh locus. Now, if it's a digital system, we use Jury's test, and for simple system, we use Routh's test. Now, taking a simple example, we'll see how Routh's test is useful. Now, if this is the given equation of system in S-plane, 5s squared plus s plus 1 upon 3s, let's take a cube plus 4s squared plus 2s plus 3. Okay, this is given. Now you see we separate it like this. Alright, so s cube, s square, s, and s raised to 0. So we take first these two, so that we take 3 and 2 first and 4 and 3 second. Alright, now the Routh's equation is basically given as b of I is equal to an minus 1 an minus 2I minus an into an minus 2I minus 1 upon an minus 1, and Ci is equal to b1 an minus 2I minus 1 minus an minus 1 bi plus 1 upon b1. So just apply this. So here we get 4 2s are 8 minus 9 by 3. So that by 4, sorry. So 1 minus 1 by 4, 0, and 3, 0. So you see the sign changes from 1 to 2, positive, negative, negative, positive. So 2 times the sign changes. So there are 2 roots in the right half S-plane, hence the system is unstable. Now if we take another example in z-plane, like we take this example, z is equal to 0, like we take g of z is equal to 0.6321 upon z minus 0.3679. Alright, now first what we gotta do is we have to find the characteristic equation. So for that we get z minus 0.3679 plus 0.6321 k is equal to 0. So what we basically do is we take the denominator, add it with the numerator multiplied by k. That's the gain. So now this is in terms of z-plane. We have to convert this into omega plane. Like you can basically just do it directly in the z-plane, but there are sometimes you'll be asked to convert it into omega plane and then map it into the omega plane to find the stability. So here what we do is we take relations between z and omega. So the relation between z and omega is z is equal to 1 plus t by 2 omega upon 1 minus t by 2 omega. Alright, so you apply this, and if we here for example we take t is equal to 1 second. Alright, so just apply t is equal to 1 second and you get 2 plus omega upon 2 minus omega. Just substitute this value in this equation of z. So what you get in the end is in terms of omega. So you get 2 plus omega 2 plus omega minus 2 minus omega. So it will be 2 plus omega minus 2 minus omega into 0.3679 0.6321 k equals to 0, because you substitute this 2 plus in terms of z and you'll get this equation. So the final equation that you'll get after solving this will be 1.3679 minus 0.6721 k into omega plus 1.264 plus 1.264 k is equal to 0. You have to just solve this equation so that you have to get everything in terms of omega. So omega you could just separate out, and you just separate out the terms without a variable and you get it 0. So you get 1 omega raised to 0. We apply Routh's equation for an omega plane. So you see that you have to keep this 1.3679 minus 0.672k 0. You need to put this 1.264 plus 1.264k and 0. So you get the stability as minus 1 is less than k is less than 2.164. So this is the value of, or the stability value of k that you get.